Did you know that World War II was won not just with bullets and bravery, but with slide rules and steel? More than 60 million people were involved in the fighting, but behind them were millions more engineers, scientists, and factory workers. They built the machines that decided the fate of the world. They created things that seemed impossible just a few years before. A single bomber, the B-29, had more than a million rivets. The United States alone produced over 300,000 aircraft and 86,000 tanks. The numbers are staggering, but what were the specific ideas, the single feats of engineering that truly tipped the scales? What were the quiet inventions, the things you don't see in the movies, that made all the difference? And what secrets about their creation are still hidden from us? Number 19, how could a simple tin can dictate the speed of an army? An army moves on its stomach, but its machines move on fuel. In the early days of the war, fuel transport was a disaster. The standard fuel containers used by the British and Americans were terrible. They were made of thin, flimsy steel. They were called petrol tins. They were rectangular and had a small handle on top. Their seams were weak and often leaked. You couldn't stack them well, they dented easily. In the hot deserts of North Africa, the sun would make the fuel expand and the tins would burst open. It's estimated that at times, British forces were losing as much as 40% of their fuel just getting it from the ports to the front lines. Think about that. Almost half of it gone, spilled into the sand. The German army had a secret weapon. It wasn't a tank or a gun, it was a fuel can. They called it the Wehrmacht's canister. It was a masterpiece of simple, practical engineering. It was made of thicker steel and had 3 handles. 3. This was the genius part. One person could carry 2 empty cans in one hand. Or 1 full can. 2 people could carry a full can between them, making long treks easier. The sides of the can had an X shape stamped into them for strength. This allowed the metal to expand and contract without breaking the seams. The spout was short, with an airtight seal and a clever air pipe that let fuel pour out smoothly, without gurgling or splashing. And inside a small air pocket was designed in, so even when full, the can would float in water. The Allies first encountered these cans and quickly realized how superior they were. An American engineer named Paul Pleiss had actually seen the design in Germany before the war and tried to get the US military interested, but they brushed him off. The British captured some of the cans during the Norwegian campaign in 1940 and immediately started to copy the design. They called their version the jerry can, a slang term for anything German. The US was slower to adopt it, first creating a version that was a poor copy with a bad cap and weak seams. But eventually, they got it right. By 1944, millions of these cans were being produced. They were strapped to every Jeep, truck, and tank. They were the lifeblood of the Allied advance across Europe after D-Day. General Patton's Third Army was famous for its rapid advances, but that speed was entirely dependent on a constant supply of fuel delivered in these simple, brilliant cans. In his book, The Guns That Last Light, Rick Atkinson describes the Red Ball Express, the massive truck convoy system that supplied the front lines. Those trucks were filled with jerry cans. It was a logistical marvel built on a foundation of well-designed sheet metal. So a simple can, an object most people would never think twice about, had a direct impact on the mobility and effectiveness of entire armies. It saved millions of gallons of fuel. It made logistics simpler and more reliable. It was a small thing that made a huge difference. But what don't we know? How many early battlefield defeats or stalled attacks can be directly attributed to the failure of the old flimsy petrol tins? Did the original German designers, working in the 1930s, have any idea their humble can would become a global standard used by their enemies to defeat them? Are there records of the exact moment a British quartermaster first held a captured German can and realized how much trouble his own army was in? Of number 18, what if you could build a bridge like a Lego set? When an army advances, it needs to cross rivers, ravines, and gorges, and when an army retreats, it often destroys the bridges behind it to slow the enemy down. During World War II, this was a constant problem. A destroyed bridge could stop an entire armored division in its tracks for days or even weeks. Engineers would have to haul in massive, heavy equipment. They would need to survey the site and custom build a new bridge from scratch. It was slow, dangerous work. The Allied forces needed something better. They needed a bridge that was fast, strong, and adaptable. The answer came from a British civil servant and amateur engineering enthusiast named Donald Bailey. He worked for the British War Office, And in his spare time, he sketched ideas. One of his hobbies was building model bridges. In 1940, during a meeting about the problem, he doodled an idea on the back of an envelope. His idea was for a modular bridge. It would be made from a series of identical, interchangeable steel panels. These panels were about 10 feet long and 5 feet high. They weren't too heavy. A group of 6 men could carry one. They could be pinned together side by side and end to end to create long trusses of any strength needed. The roadway or deck was made of wooden planks that were laid across the bottom of these trusses. This was the Bailey Bridge. Its genius was its simplicity and modularity. You didn't need heavy cranes to build it, though they helped. A team of engineers could assemble it by hand. They would build the bridge on one side of the river and then use rollers to push it across the gap. It was like a giant heavy-duty construction set. If you needed a stronger bridge to carry tanks, you could bolt more panels onto the sides, making the trusses thicker. You could even stack panels on top of each other. Double Bailey Bridge, 2 panels wide and 2 high, could support the heaviest tanks of the war. The Bailey Bridge was first used in North Africa in 1942. It was a huge success. The Royal Engineers became masters at assembling them at incredible speeds. In Italy, a country filled with mountains and rivers, over 3,000 Bailey bridges were built. After D-Day, they were essential for the push into Germany. As fast as the German army blew up bridges, the Allies could put up a Bailey Bridge to replace it. Field Marshal Bernard Montgomery said the Bailey Bridge was one of the 3 pieces of equipment that made the Allied victory possible, alongside the Jeep and the C-47 transport plane. The historian Stephen E. Ambrose, in his book Citizen Soldiers, repeatedly highlights how these bridges kept the supply lines open and the armies moving. The U.S. produced so many Bailey Bridge components that they were used all over the world. It was a simple idea born on the back of an envelope that solved one of the most fundamental problems of military logistics. It allowed armies to maintain their momentum, which in war is everything. But what crucial details are lost to history? What was the failure rate of the first prototype Bailey bridges during testing, and what were the near catastrophic flaws they discovered? Are there any surviving personal diaries of the engineers who built these bridges under fire, detailing the close calls and improvised techniques they had to invent on the spot? How many of Donald Bailey's other doodles were brilliant ideas that were never even considered? Number 17, how do you invade a continent without a port? By 1944, the Allies were ready to invade France. The plan was codenamed Operation Overlord. It would be the largest amphibious invasion in history. But there was a colossal problem. To supply millions of soldiers, you need a deep water port, you need docks and cranes to unload thousands of tons of supplies every single day. Food, ammunition, fuel, vehicles, everything. But the major French ports like Cherbourg and Le Havre were heavily defended. The German forces knew how important they were. They would be the last places to fall, and they would be destroyed in the fighting. Taking a port could take weeks. The invasion force couldn't wait that long. They would run out of supplies and be pushed back into the sea. The solution was audacious. It was almost insane. If you can't capture a port, why not bring one with you? This was the idea behind the Mulberry Harbors. The plan was to prefabricate 2 entire artificial harbors in Britain, tow them across the English Channel in pieces, and assemble them off the coast of Normandy. It was a project of unimaginable scale. The chief architect was Professor J.D. Bernal, a scientist, but the project involved thousands of engineers, construction workers, and military planners. The details are laid out in Guy Harkup's book, Codename Mulberry. The harbor had several key components. First, a breakwater was needed to calm the notoriously rough waters of the channel. This was made by sinking old ships called corncobs and massive hollow concrete caissons called phoenixes. These phoenixes were huge, like floating buildings up to 6 stories high. They had to be towed across the channel by tugboats and then sunk precisely in place by flooding them with water. Inside this calm water, they built floating roadways codenamed whales. These were long steel bridges that rested on floating pontoons called beetles. These roadways connected a series of pierheads, or spuds, which were platforms that could be raised and lowered with the tide. This meant ships could unload their cargo onto the piers, which would then be driven to the beaches along the floating roadways. The construction was a massive secret. The components were built in docks and harbors all across Britain. People living nearby had no idea they were looking at pieces of an artificial port. The day after D-Day, on June 7, 1944, the fleet of tugboats began the slow, dangerous journey of towing these giant concrete and steel pieces across the channel. It was a race against time. Two harbors were built, Mulberry A at Omaha Beach for the Americans and Mulberry B at Arromanches for the British and Canadians. For a short time, they worked, but then on June 19th, a massive storm, the worst in 40 years, hit the Normandy coast. It raged for 3 days. Mulberry A, the American harbor, was completely destroyed. It was a devastating blow. But Mulberry B, which was slightly more sheltered, survived. It was repaired and reinforced, and it became the single most important port for the Allied invasion. In the months that followed, it was used to land over 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. It was nicknamed Port Winston, and it was the logistical lifeline that allowed the Allies to build up their forces in France and eventually break out of Normandy. Without it, the invasion might have failed. But what engineering secrets remain? What were the alternative, even crazier, designs for the artificial harbors that were rejected? How many workers died in accidents during the secret construction of the massive Phoenix caissons, and were their deaths covered up to maintain morale? Are there classified reports detailing the exact reasons why Mulberry A failed so catastrophically in the storm while Mulberry B survived? Was it just luck or a subtle flaw in the American construction and assembly? Number 16, what happens when your enemy controls your rubber supply? Modern warfare runs on rubber. Tires for every truck, jeep, and airplane. Hoses, seals, and gaskets in every engine. Waterproof clothing and boots for soldiers. In 1941, the United States needed a huge amount of rubber, but over 90% of the world's natural rubber came from plantations in Southeast Asia. Then, in late 1941 and early 1942, Japan conquered these regions. Suddenly, the Allies were cut off from their primary source of a critical strategic material. The existing stockpile in the US was only about 1 year's worth of civilian consumption, let alone the massive needs of a global war. This was a crisis, a full-blown emergency. The solution had to be a massive feat of chemical engineering, create a synthetic rubber industry from almost nothing. Scientists had known how to make synthetic rubber in a lab for years. German scientists had developed a version called Buna rubber in the 1930s. But making it in a laboratory is one thing. Producing hundreds of thousands of tons of it in a factory is another. The challenge was immense. It required building a nationwide network of factories to produce the raw chemical components like butadiene and styrene, and then other factories to combine them into a usable synthetic rubber. President Franklin D. Roosevelt created the Rubber Reserve Company and put a man named William M. Jeffers in charge of the program. Well, Jeffers wasn't a scientist, he was the president of the Union Pacific Railroad. He was a tough, no-nonsense manager who knew how to get huge projects done. The government partnered with the big four tire companies, Goodyear, Goodrich, Firestone, and U.S. Rubbering, as well as oil and chemical companies like Standard Oil. They pooled their patents and knowledge, a rare act of cooperation forced by the national emergency. The story is detailed in books like Freedom's Forge by Arthur Herman. They decided to standardize on one specific type of synthetic rubber called Government Rubber Styrene, or GRS. Then, they began a frantic construction program. Over 50 new factories were built across the country. It was one of the fastest and largest government construction projects in American history, costing over $700 million at the time. Meanwhile, the government had to ration rubber at home. A national speed limit of 35 miles per hour was imposed to save tire wear. Citizens were asked to turn in any old rubber they had, tires, garden hoses, raincoats, and massive scrap drives. The program was a stunning success. By 1944, U.S. production of synthetic rubber exceeded 800,000 tons per year. That was more than the country's entire pre-war consumption of natural rubber. The new synthetic rubber wasn't perfect. It was less elastic and built up more heat than natural rubber, which was a problem for heavy-duty tires on bombers. Scientists had to work frantically to improve the formulas and develop new tire designs, but it worked. It kept the Allied war machine rolling, flying, and fighting. Without this monumental engineering and industrial effort, the lack of rubber could have paralyzed the Allied armies. But what if the program had failed? What were the biggest chemical explosions or industrial accidents at these new, hastily built plants, and how were they kept from the public? Are there records of the secret research into even more radical alternative sources of rubber, like the Russian dandelion plant, that were pursued as backup plans? How close did the program come to missing its deadlines? And what were the desperate, last-minute engineering shortcuts they had to take to make it work? Number 15. How can a single soldier destroy a 40-ton tank? In the early years of the war, the foot soldier, the infantryman, was terrified of tanks. A tank was a steel monster. It was impervious to rifle fire and machine guns. The only way to stop one was with a big anti-tank gun, which was heavy, hard to move, and needed a whole crew to operate. If a tank broke through the lines and got in among the infantry, it could cause chaos and devastation. What the ordinary soldier needed was a personal portable weapon that could kill a tank. The answer came from the United States Army. It was a simple rocket launcher, officially called the M1 rocket launcher, but everyone called it the bazooka. The name came from its resemblance to a strange homemade musical instrument played by radio comedian Bob Burns. The weapon was developed at the Ordnance Department by a team that included Colonel Leslie Skinner and Edward Ohl. The key innovation was combining two existing technologies, a man-portable rocket and a shaped charge warhead. A shaped charge is a clever way to use explosives. Instead of just exploding outwards in all directions, the explosive is shaped around a cone-shaped metal liner, usually copper. When the explosive detonates, it collapses the cone into a superheated, super-fast jet of molten metal. This jet can travel at several miles per second. It doesn't punch a big hole in armor. It burns and blasts a small hole through it, sending a spray of molten metal and shrapnel into the tank's interior. This could ignite fuel or ammunition and kill the crew. This technology, known as the Monroe effect, had been around since the 1880s, but putting it into a small, stable rocket was the challenge. The launcher itself was just a simple steel tube, about 5 feet long, open at both ends. It had a simple sight and a shoulder rest. A two-man team operated it. One man, the gunner, aimed it. The other man, the loader, slid a 3.5-pound rocket into the back of the tube and connected 2 wires to complete the electrical firing circuit. When the gunner pulled the trigger, a battery ignited the rocket motor and it flew out of the tube. The backblast was significant, so the loader had to be careful where he stood. The bazooka first saw action in North Africa during the Operation Torch landings in 1942. The results were immediate and dramatic. A small team of soldiers could now hide in a ditch or a building and ambush and destroy a powerful tank. It was a force multiplier. It gave the infantry a fighting chance. General Dwight D. Eisenhower was so impressed that he ordered it to be rushed into mass production. As detailed in Ian V. Hogg's The Encyclopedia of Infantry Weapons of World War II, over 400,000 bazookas were produced. They were given to every army in the Allied forces. The German army was so impressed by captured bazookas that they reverse-engineered them to create their own, more powerful version called the Panzerschreck. The bazooka wasn't a perfect weapon, it had a short range, and the rocket was slow, so hitting a moving target was difficult. Early versions had problems with the battery-powered ignition system, but it changed the dynamic of infantry combat. It democratized anti-tank warfare. The psychological effect was just as important as the physical one. Tank crews could no longer feel invincible when operating near enemy infantry. Any soldier hiding in a foxhole could be carrying a tank killer. But what do we still not know? How many friendly fire incidents were caused by the bazooka's dangerous backblast in the confusion of combat, and were these statistics suppressed? What were the most unusual or improvised uses of the bazooka on the battlefield for tasks it was never designed for? Are there any surviving design documents for the competing and ultimately failed anti-tank weapons that the bazooka beat out to become the standard? Number 14, how did a pressurized cabin change the war in the Pacific? By 1944, the war in the Pacific was reaching its climax. The United States was preparing for the final assault on the Japanese home islands. To do this, they needed a new kind of bomber. They needed a plane that could fly higher, faster, and farther than any bomber ever built before. It had to fly from new air bases in the Mariana Islands, like Saipan and Tinian, all the way to Tokyo and back. That's a round trip of almost 3,000 miles, mostly over open ocean. It had to fly above 30,000 feet, higher than Japanese fighter planes and anti-aircraft fire could effectively reach. The plane they built was the Boeing B-29 Superfortress. It was the most complex and expensive weapon of the entire war. The development program cost over $3 billion. The Manhattan Project, which built the atomic bomb, cost $2 billion. The B-29 was a technological marvel, But one single engineering feat stood out above all others: its fully pressurized crew cabin. Flying at 30,000 feet is brutal. The air is thin, with not enough oxygen to breathe. The temperature is 40 degrees below zero. In previous bombers like the B-17, the crew had to wear heavy, fleece-lined flight suits, clumsy oxygen masks, and heated gloves just to survive. They were constantly cold, tired, and struggling with hypoxia. It was incredibly inefficient and exhausting. A 10-hour mission was a physical ordeal. The B-29 changed all that. Boeing engineers designed the plane with 3 separate pressurized compartments, one for the pilots in the cockpit, one for the gunners and navigator in the middle of the plane, and one for the tail gunner at the very back. These compartments were sealed like the hull of a submarine. Air was pumped into them by compressors driven by the engines, keeping the internal cabin altitude at a comfortable 8,000 feet, even when the plane was flying at 30,000 feet. The crew could work in their regular uniforms without oxygen masks. They were warmer, more comfortable, and could think more clearly. The forward and middle compartments were connected by a long, narrow tunnel that ran over the unpressurized bomb bays. A crew member could crawl through this tunnel to move between sections of the plane. This was an incredibly difficult engineering challenge. The skin of the plane had to be strong enough to withstand the constant pressure difference between the inside and the outside. Every window, door, and control cable entry had to be perfectly sealed. Another revolutionary feature tied to this was the remote-controlled gun system. Instead of sitting and freezing wind-blasted turrets, the gunners sat inside the pressurized cabin at computer-controlled sighting stations. They aimed using a remote sight, and analog computers automatically calculated the lead, wind drift, and parallax for the machine guns in the remote turrets. It was a science fiction weapon for its time. The B-29's operational history is documented in books like Super Fortress by Curtis LeMay and Bill Yen. Its high-altitude performance allowed it to conduct a devastating bombing campaign against Japan. It was the only aircraft capable of carrying and delivering the atomic bombs that were dropped on Hiroshima and Nagasaki, effectively ending the war. The pressurization system was the key that unlocked this high-altitude capability. It was a human-focused piece of engineering that made the machine more effective by making the crew more effective. But what are the untold stories? How many test pilots were killed or injured in early B-29 prototypes when the pressurization systems failed catastrophically at high altitude? Are there classified reports on the psychological effects of being sealed in a pressurized tube for 15 hours and how it affected crew cohesion and combat performance? What were the desperate improvised repairs that flight engineers had to make in midair when a seal blew or a window cracked over the middle of the Pacific Ocean? Number 13, what does it take to mass produce a miracle drug? In previous wars, more soldiers died from infection than from enemy bullets. A simple wound from a piece of shrapnel could get infected, lead to gangrene, and result in a painful amputation or a slow death. Medical science was a critical part of the war effort, and the Holy Grail was a drug that could kill bacteria. That drug was penicillin. Penicillin was discovered by accident in 1928 by a Scottish scientist named Alexander Fleming. He noticed that a mold, Penicillium notatum, was killing bacteria in a petri dish, but he couldn't produce enough of the active substance to be medically useful. It remained a laboratory curiosity for over a decade. In the late 1930s, a team at Oxford University, led by Howard Florey and Ernst Chain, figured out how to purify penicillin and proved it could cure bacterial infections in animals and then humans. But the problem was production. The process was incredibly difficult. They were growing the mold in small flasks. It would take thousands of flasks to produce enough penicillin to treat just one person. With a world war raging, this was not a solution. In 1941, Florey and a colleague traveled to the United States to ask for help. They went to the Department of Agriculture's research lab in Peoria, Illinois. This is where the engineering challenge was tackled. The problem was twofold: they needed a better strain of the mold, and they needed a better way to grow it. A worldwide search for a more productive strain of penicillin began. The strain that became the ancestor for almost all the world's penicillin production was famously found on a moldy cantaloupe melon in a Peoria market. Researchers then used X-rays and ultraviolet light to create mutated versions of this mold that produced even more penicillin. The second problem was industrial. How do you grow this mold on a massive scale? The key was to move from surface culture in flasks to deep tank fermentation. This meant growing the mold in huge, sterile vats filled with a nutrient broth, like a brewery. This was a massive engineering problem. The vats, some holding 10,000 gallons, had to be kept perfectly sterile. Any contamination by outside bacteria would ruin the batch. They needed complex systems of pipes, valves, and agitators to stir the mixture and pump in sterilized air. The temperature had to be precisely controlled. Chemical engineers from companies like Pfizer, Merck, and Squibb were brought in to solve these problems. As documented in Eric Lax's book, The Mold in Dr. Flory's Coat, it was a frantic collaborative effort between government, academia, and industry. By 1943, they had cracked the code. Factories were built and production skyrocketed. By the time of the D-Day invasion in June 1944, there was enough penicillin available to treat every single Allied soldier who needed it. It was a miracle. Soldiers who would have certainly died from infected wounds were saved. It dramatically lowered the death rate from injuries and diseases like pneumonia. Penicillin didn't just save lives. It returned soldiers to the fight, preserving the combat strength of Allied units. It was a triumph of biochemical engineering that changed the face of medicine and warfare forever. But what secrets lie in the archives? Were there rival research teams working on other miracle drugs that failed, and have their stories been forgotten? How many of the early desperate human trials of penicillin resulted in death or severe side effects due to impure batches? Are there classified records detailing the attempts by Axis powers to steal the secrets of penicillin production through espionage? Number 12. How did a farm implement maker help invade Europe? For the D-Day landings to succeed, the Allies had to get hundreds of thousands of men and their equipment from ships onto the hostile beaches of Normandy. They needed a special kind of boat. It had to be able to carry a platoon of soldiers or a vehicle like a jeep. It needed a shallow draft so it could run right up onto the beach, and it needed a way to get the men and cargo off quickly under fire. The existing landing craft designs were not good enough. The man who solved this problem was not a naval architect. He was a brash, innovative boat builder from New Orleans named Andrew Jackson Higgins. Higgins Industries built specialized, shallow draft boats for loggers and oil drillers working in the swamps and bayous of Louisiana. His boats had a protected propeller and a semi-flat bottom, which allowed them to operate in very shallow water and even run over logs without damage. This design was called the Eureka boat. The U.S. Marine Corps saw its potential and started testing it. The Marines liked the boat, but they had a crucial suggestion. They had seen pictures of Japanese landing craft that had a ramp at the front. This was a much better design than having soldiers jump over the high sides of the boat, exposing themselves to enemy fire. Higgins and his chief engineer took this idea and incorporated it into the Eureka boat. They designed a wide steel ramp at the bow that could be quickly lowered. Now, a full platoon of 36 men could run straight out onto the beach. A jeep could be driven directly onto the sand. This new design was called the LCVP Landing Craft Vehicle Personnel. Everyone just called it the Higgins boat. The genius of the Higgins boat was its simple, rugged design. It was made mostly of wood, specifically plywood, which was a non-strategic material. This was important because steel was in high demand for warships and tanks. The design was easy to build, which meant they could be mass-produced at an incredible rate. Higgins transformed his company, hiring tens of thousands of workers from all backgrounds, including women and African Americans, in a fully integrated workforce, which was rare at the time. His factories in New Orleans ran 24 hours a day, churning out thousands of these boats. As detailed in Jerry E. Strahan's book, Andrew Jackson Higgins and the Boats That Won World War II, over 20,000 Higgins boats were built. On D-Day, June 6, 1944, the Higgins boat was the workhorse of the invasion. It carried the first waves of American, British, and Canadian soldiers to Omaha, Utah, Gold, Juneau, and Sword beaches. Dwight D. Eisenhower himself said, "Andrew Higgins is the man who won the war for us." He argued that if Higgins hadn't designed and built those LCVPs, the entire strategy for the war would have been different. They couldn't have landed over open beaches. They would have had to attack heavily defended ports with much higher casualties. The Higgins boat was a simple, practical piece of engineering that made the liberation of Europe possible. But what don't we know about this iconic boat? How many different prototype designs for the ramp mechanism failed during testing, and were there any near-fatal accidents? Are there any surviving interviews with the factory workers who built these boats, describing the pressure and the pace of production? What were the specific design flaws that were discovered in combat, and how did crews in the field have to modify their boats to survive? Number 11, how do you make a shell explode at the perfect time? Artillery and anti-aircraft guns fire shells that are supposed to explode before they hit the ground, showering the enemy with shrapnel. For decades, the only way to do this was with a time fuse. This was like a little mechanical clock in the nose of the shell. Before firing, a gunner would set the fuse to explode after a certain number of seconds. But this was incredibly difficult to get right. You had to estimate the range to the target perfectly. A small error in the calculation, a change in wind, or a slight variation in the propellant charge could mean the shell exploded too high and was useless, or too low and buried itself in the ground before detonating. Against a fast-moving airplane, it was almost impossible. The Allies developed a secret weapon that solved this problem. It was one of the most significant inventions of the war. It was called the proximity fuse, or VT fuse for variable time. It was a tiny, self-contained radar set, small enough to fit into the nose of an artillery shell. This was a mind-boggling feat of engineering. The fuse contained a small radio transmitter and receiver. As the shell flew through the air, the transmitter sent out radio waves. These waves would bounce off a target, an airplane, or the ground and be picked up by the receiver. By measuring the change in frequency of the reflected waves, the Doppler effect, the fuse could determine when it was getting close to the target. At the perfect moment, it would trigger the explosion. The challenge was making this device. It had to be tiny and incredibly rugged. The components, vacuum tubes, batteries, circuits had to survive being fired from a cannon. The forces inside a gun barrel are immense, over 20,000 times the force of gravity. The shell is also spinning at thousands of revolutions per minute. Early vacuum tubes shattered instantly. The team of scientists, led by Merle Tuve at the Johns Hopkins University Applied Physics Laboratory, had to essentially reinvent electronics. They developed new, miniature, shock-proof vacuum tubes that looked like tiny acorns. They created a special battery that was activated by the shock of firing, its liquid electrolyte stored in a glass ampule that would shatter upon acceleration. The project, as described in Ralph Baldwin's book, The Deadly Fuse, was a massive undertaking involving over 100 different companies and university labs. The proximity fuse was first used by the U.S. Navy in 1943. It was devastatingly effective. In anti-aircraft warfare, it increased the kill rate against enemy planes by a factor of 3 or more. The fuses were kept a closely guarded secret. They were not allowed to be used over land where a dud shell could be recovered by the enemy. But during the Battle of the Bulge in late 1944, with the German army making a surprise offensive, General Eisenhower authorized their use in land artillery. The effect was terrifying. American artillery shells began exploding in the air, right above the heads of the German soldiers who were advancing through the forests of the Ardennes. They had never seen anything like it. It was a key factor in breaking up the German attack. One captured German officer reportedly said the new shell was the most demoralizing and destructive weapon they had faced. But what are the hidden stories behind this invention? How many scientists were injured or killed in lab accidents while testing these highly sensitive electronic fuses? Were there any instances of espionage where rival powers came close to stealing the design, and how were they stopped? Are there any battlefield reports detailing the initial confusion and fear among Allied soldiers who first witnessed their own artillery behaving in this strange, new, and deadly way? Number 10. How did an engine from a fighter plane make a bomber great? The Avro Lancaster was the most famous and successful heavy bomber of the Royal Air Force's Bomber Command. It was a beast of an aircraft with a huge, unobstructed bomb bay that could carry the largest bombs of the war, including the 12,000-pound Tallboy and the 22,000-pound Grand Slam earthquake bombs. The Lancasters dropped over 600,000 tons of bombs on enemy territory, but the Lancaster owed its existence and its incredible performance to one thing: its engines. Specifically, the Rolls-Royce Merlin engine. The Merlin was a liquid-cooled V12 piston engine. It was an engineering masterpiece. It was originally designed in the 1930s by a team led by Arthur Rubra and Stanley Hooker. It was the engine that powered the Hawker Hurricane and the Supermarine Spitfire, the fighter planes that won the Battle of Britain. It was powerful, reliable, and, most importantly, constantly being improved. The real genius of the Merlin was its supercharger. A supercharger is essentially a compressor that forces more air into the engine cylinders. More air means you can burn more fuel, which means you get more power. At high altitudes where the air is thin, a good supercharger is essential. The Lancaster was actually born from a failed bomber, the Avro Manchester. The Manchester was designed with two of the new, very powerful, but deeply unreliable Rolls-Royce Vulture engines. The Vulture was basically two smaller engines bolted together, and it was plagued with problems, especially overheating. The Manchester was a disaster. So the designer, Roy Chadwick, made a bold decision. He redesigned the wing to hold four of the proven, reliable Merlin engines instead of two of the unreliable Vultures. The result was the Lancaster. With four Merlins, it could fly higher, faster, and carry a heavier bomb load than any other bomber in the RAF. Throughout the war, Rolls-Royce engineers kept improving the Merlin. They developed a two-speed supercharger. This was like having a gearbox for the supercharger. It used one gear for low altitudes and automatically shifted to a higher gear for high altitudes. This gave the engine incredible performance across a wide range of altitudes. As documented in Leo McKinstry's book, Lancaster, the Second World War's Greatest Bomber, these improvements were a constant race. As enemy fighter technology improved, the bombers had to fly higher and faster to survive. The improvements to the Merlin engine allowed them to do that. The Lancaster's ability to operate at night at high altitude was entirely dependent on the performance and reliability of its four Merlin engines. The Merlin engine was so good that it was also licensed for production in the United States by the Packard Motor Car Company. These American-built Merlins would go on to power one of the most iconic aircraft of the war, the P-51 Mustang. But for the British, the Merlin was the heart of their strategic bombing campaign. It was the sound of the RAF's nightly offensive against the industrial heartland of the German war machine. Over 150,000 Merlin engines were built. It was a triumph of mechanical engineering that powered two of the most important aircraft of the war, a fighter that saved Britain, and a bomber that helped crush the enemy. But what are the forgotten technical details? What were the specific catastrophic failure modes of the early Merlin engines? And how did engineers in the field develop quick fixes to keep the planes flying? Are there any surviving logbooks from test engineers at Rolls-Royce that detail the heart-stopping moments when a new supercharger design was pushed to its limits and nearly exploded? How many design arguments and personality clashes occurred between the brilliant but stubborn engineers at Rolls-Royce, and how did these conflicts ultimately shape the final design of the engine? Number 9. Can you win a war with quantity over quality? The German army had some of the most feared tanks of the war. The Tiger and the Panther were technologically advanced machines. They had thick, sloped armor that was almost impossible to penetrate. They had powerful, high-velocity 88mm guns that could destroy an Allied tank from over a mile away. On a one-to-one basis, the standard American tank, the M4 Sherman, was no match for them. So how did the Allies win the ground war in Europe? The answer lies in a different kind of engineering. The engineering of mass production. The M4 Sherman was not the best tank of the war, but it was arguably the most important. Its design philosophy was completely different from the German approach. The Germans focused on technological superiority, creating complex, heavy tanks that were expensive and slow to build. The Americans focused on producing a good enough tank in overwhelming numbers. The Sherman was designed from the ground up to be easy to manufacture, easy to transport, and easy to repair. The engineering behind the Sherman was practical. It used a standardized chassis that could be fitted with different turrets and guns. It was powered by a reliable aircraft-style radial engine, and later by other engines, including a diesel. Its parts were interchangeable. A key feature was its vertical volute spring suspension, which was simple and easy to maintain in the field. As described in books like Armored Thunderbolt by Steven Zaloga, the real weapon was not the tank itself, but the American factory system that built it. Companies like Ford, General Motors, and Chrysler, the giants of the automobile industry, turned their full power to building tanks. They used assembly line techniques to churn out Shermans at an astonishing rate. The numbers tell the story. The Germans built about 1,300 Tiger I tanks and about 6,000 Panther tanks during the entire war. The United States built nearly 50,000 Sherman tanks. The Allies could afford to lose Shermans in battle because there were always more coming. The standard tactic for a platoon of 5 Shermans encountering a single Tiger was for 4 of them to attack from the front, drawing its fire, while the 5th tried to maneuver to the side or rear to get a shot at its weaker armor. Often, several Shermans would be destroyed in the process. It was a brutal, costly calculus, but it worked because of the sheer weight of numbers. The Sherman also had advantages. It was much more mechanically reliable than the complex German tanks, which were prone to breakdowns. It was faster and more maneuverable, and it was constantly being upgraded. Later versions were fitted with a more powerful 76mm gun and had improved armor and suspension. The Sherman was a versatile platform used not just as a battle tank but also as a tank destroyer, a recovery vehicle, and even a platform for rocket launchers. It was the backbone of the Allied armored forces on every front, from the deserts of Africa to the islands of the Pacific and the fields of France. It was a victory of industrial engineering. But what questions remain unanswered? What were the fiercest internal debates within the U.S. Army Ordnance Department between the engineers who wanted a better quality tank versus those who prioritized mass production? Are there records of the exact failure rates of Sherman tank components, and how did this data secretly drive the continuous design improvements? How many Sherman crews developed unauthorized, field-expedient modifications to their tanks to improve their chances of survival? And what were the most ingenious of these battlefield inventions? Number 8, how did a single invention turn night into day for Allied pilots? In the early years of the war, flying at night was a guessing game. Pilots had to rely on a confusing array of glowing dials in the cockpit. This caused eye strain and fatigue. Looking down at the bright instruments would ruin a pilot's night vision, making it hard to see enemy aircraft or targets outside the cockpit. Looking outside for too long meant losing track of the plane's speed, altitude, and direction. This constant shifting of focus was inefficient and dangerous. The solution was an ingenious piece of optical and lighting engineering. The British Royal Aircraft Establishment at Farnborough developed a system to illuminate the cockpit with red light. They discovered that red light has a minimal effect on the human eye's ability to adapt to the dark, but just flooding the cockpit with red light wasn't enough. The instruments themselves needed to be changed. The old method of painting numbers with glowing radium paint was not ideal. The glow was often too bright or too dim. The breakthrough was ultraviolet lighting. Small lamps were installed in the cockpit that emitted UV light, which is invisible to the human eye. The needles and markings on the instruments were then painted with a special fluorescent paint. When the UV light hit this paint, it would glow with a clear, steady, but soft reddish-orange light. This meant the instruments were perfectly visible, but they didn't create any glare. A pilot could look at their instruments and then look outside into the darkness without losing their night vision. It was a simple but transformative idea. But there was another problem. Cockpit canopies are made of curved plastic or glass. They act like a mirror at night, reflecting the light from the instruments back into the pilot's eyes. This was a major distraction, so engineers developed a second innovation, the cockpit canopy sunshade. It was a simple roller blind, but instead of being opaque, it was made of a tinted plastic. During the day, it could be pulled down to reduce sun glare. At night, it was pulled down to act as a filter. The pilot would look at his instruments through the tinted shade. This shade was angled so that it blocked any reflections from the canopy. It also had a small cutout at the top, so the pilot could look over it to use his gun sight. These two innovations, UV instrument lighting and the canopy shade face, were standardized across the RAF and later adopted by the USAF. They made night flying significantly safer and more effective. Night fighter pilots could hunt their prey more effectively. The bomber crews could navigate more accurately and were less fatigued on long missions. This is one of those quiet, unglamorous feats of engineering that you never hear about, but which had a direct impact on the performance of thousands of airmen. The details of these systems are often found only in obscure technical manuals and pilot training notes from the era, like the Air Publication 730B PN. It was human factors engineering at its best, designing the machine to work better with the human operator. But what are the missing pieces of this story? Were there alternative lighting systems tested, like green or blue light, that failed for reasons that are not well documented? How many flying accidents in the early war can be directly attributed to pilot disorientation caused by poor cockpit lighting? Are there any surviving personal accounts from the engineers at Farnborough describing the eureka moment when they solved the reflection problem with the simple sunshade idea? Number 7. How did a wooden plane become one of the fastest aircraft of the war? In an age of all-metal warplanes, the idea of building a frontline bomber out of wood seemed crazy. The wood was seen as old-fashioned, a material for biplanes from a bygone era. But during World War II, a British company, de Havilland, designed and built one of the most remarkable aircraft of the entire conflict, the Mosquito. And it was made almost entirely of wood. The de Havilland Mosquito was the brainchild of Geoffrey de Havilland. His idea, proposed in 1938, was radical. He believed he could build a bomber so fast that it wouldn't need any defensive guns. It could outrun enemy fighters. To achieve this speed, it had to be incredibly light and aerodynamically clean. The best way to do this, he argued, was to build it from wood. A wooden structure could be molded into very smooth, complex curves, reducing drag. And it would be very light. The Air Ministry was skeptical. They were focused on heavy, four-engine bombers with multiple gun turrets. But de Havilland persisted. The engineering of the Mosquito was brilliant. The fuselage was built like a canoe, in two separate halves, left and right. It was a sandwich construction. A layer of balsa wood was placed between two thin sheets of birch plywood. These layers were glued and pressed together in a concrete mold to create a strong, light, and perfectly smooth shell. All the internal wiring, control cables, and equipment were installed in the two halves while they were still open. And then the two halves were glued and screwed together. This made it incredibly easy to assemble. The wings were also made of wood, with spruce spars and a plywood skin. Because it had no gun turrets, the fuselage was incredibly streamlined, and it was powered by two of the same Rolls-Royce Merlin engines that powered the Spitfire and the Lancaster. The result was astonishing. The Mosquito was one of the fastest aircraft in the world when it entered service in 1941. Early bomber versions could fly at nearly 400 miles per hour, faster than the frontline German fighter, the Messerschmitt Bf 109. It could carry a 4,000-pound bomb load all the way to Berlin. The German Air Force was shocked. Their fighters couldn't catch it. Hermann Göring, the head of the Luftwaffe, was famously furious about the Mosquito. He complained that it was built by piano makers and was faster than his best planes. The use of wood had another huge advantage. Britain was facing a shortage of strategic metals like aluminum, but it had plenty of wood, and skilled woodworkers, furniture makers, cabinet makers, and piano builders were all put to work building Mosquito components. The plane's versatility was also amazing. It was used as a high-speed bomber, a night fighter, a pathfinder to mark targets for the main bomber force, and a photo reconnaissance aircraft. The story of its development is told in books like Mosquito, the original multi-role combat aircraft by Graham M. Simons. It was a triumph of unconventional thinking and clever structural engineering, but what secrets about the wooden wonder are still hidden? What were the catastrophic structural failures that occurred during early prototype testing, and how did they secretly reinforce the design? Are there classified reports on the Mosquito's vulnerability to certain types of weather, like tropical humidity, which could weaken the glue holding the wooden structure together? How many different types of glue were tested, and what was the secret formula of the one they finally chose for its strength and durability? Number 6. What if an artillery shell could think for itself? One of the greatest challenges in warfare is hitting a moving target. For a battleship defending against an enemy aircraft, or a soldier trying to shoot down a diving bomber, the problem is the same. You have to aim not at the target, but where the target is going to be. This requires incredible skill, and even then, it's mostly luck. During the early part of the war, anti-aircraft gunnery was shockingly ineffective. It could take thousands, even tens of thousands of shells to shoot down a single plane. The military needed a way to aim better. The solution was a mechanical brain, an analog computer. These devices were called gun directors. One of the most advanced was the Kerosene director, developed by the British. But the Americans took the idea to a whole new level with the M9 gun director, developed at Bell Telephone Laboratories. The M9 was a complex and brilliant piece of electromechanical engineering. It was an analog computer designed to do one thing: solve the complex trigonometric problem of anti-aircraft gunnery in real time. Here's how it worked. The M9 was connected to a radar set, which provided a continuous stream of data on the target's range, altitude, and bearing. The human operators would also track the target visually through telescopes connected to the director. The M9 took all this information and, through an incredible array of gears, cams, rotating shafts, and electrical amplifiers, it calculated the target's speed and flight path. But it didn't stop there. It then calculated where the target would be in the future, taking into account the time it would take for the shell to travel from the gun to the target. It also factored in variables like wind speed, air density, and even the curvature of the Earth. The output of this complex calculation was a set of electrical signals. These signals were sent to the anti-aircraft guns, usually a battery of 4 90mm cannons. The signals controlled electric and hydraulic motors on the guns, automatically aiming them at the correct spot in the sky. The gun crew's only job was to load the shells. The M9 did all the thinking. It was a revolutionary system. The details of its inner workings are highly technical, found in declassified Bell Labs technical journals from the period. The M9, combined with the proximity fuse, transformed anti-aircraft defense. It was a deadly combination. The M9 pointed the gun to the right place, and the proximity fuse made sure the shell exploded at the right time. This system was particularly effective against the German V-1 flying bomb attacks on London in 1944. These were fast, small, unmanned jets, very difficult to hit. At first, fighter planes and older gun systems had little success. But then, batteries of 90mm guns controlled by M9 directors and using proximity fuses were moved to the coast. The kill rate shot up dramatically. In the last week of the V1 campaign, these gun batteries were shooting down over 80% of the V1s that entered their range. It was a stunning demonstration of automated, computer-controlled warfare, but what mysteries remain about these mechanical brains? What were the strangest bugs or calculation errors that early analog computers like the M9 produced, and what were the bizarre aiming solutions they sometimes generated? How many brilliant mathematicians and engineers who worked on these secret projects at Bell Labs received no public credit for their work due to wartime secrecy? Are there any surviving schematics for the even more advanced, next-generation gun directors that were on the drawing board when the war ended? Number 5. How could a single fighter plane dominate the skies of Europe? In 1943, the American bombing campaign against Germany was in deep trouble. The B-17 Flying Fortress bombers were flying deep into enemy territory, but they were flying alone. The fighter planes that were supposed to protect them, like the P-47 Thunderbolt and the P-38 Lightning, did not have enough range to escort them all the way to targets deep inside Germany and back. Once the escorts had to turn back, the German fighter planes would swarm the bomber formations. The losses were catastrophic. The 8th Air Force was being bled white. They desperately needed a long-range escort fighter. The plane that saved the day was the North American P-51 Mustang. But the P-51 that first flew was a good plane, not a great one. It used an Allison engine that performed poorly at high altitudes, which is exactly where the bombers needed protection. The Mustang was fast down low, but sluggish up high. The British, who had first ordered the plane, saw its potential. They decided to try an experiment. They took a Mustang and replaced its American Allison engine with their own high-performance engine, the Rolls-Royce Merlin. The same engine that powered the Spitfire. The result was magic. The combination of the Mustang's advanced aerodynamic airframe and the Merlin's high-altitude power, especially with its two-stage supercharger, created a war-winning weapon. The new plane was called the P-51B. It was incredibly fast, highly maneuverable, and most importantly, it had incredible range. With the addition of external drop tanks, it could fly all the way from England to Berlin and back. The Packard Company in the US began mass-producing a licensed version of the Merlin engine, and the P-51D, with its iconic bubble canopy, began rolling off the assembly lines. The engineering of the Mustang was superb. It had a laminar flow wing, a new airfoil design that significantly reduced drag, making it faster and more fuel efficient. This was a key part of its long-range capability. The bubble canopy on the D model was another critical innovation. It gave the pilot a 360-degree unobstructed view, which is a massive advantage in a dogfight. The details of this transformation are covered in books like Mustang: The Story of the P-51 Fighter by Robert W. Gruenhagen. When the Merlin-powered Mustangs arrived in Europe in force in early 1944, they changed the air war completely. Now, the bombers had a little friend that could stay with them all the way to the target and back. The Mustang pilots didn't just defend the bombers, they went on the offensive. They hunted the German fighters, attacking them as they tried to form up and even strafing them on their own airfields. The German Air Force, the Luftwaffe, was decimated. They lost their best pilots and planes in a brutal war of attrition. By the time of the D-Day invasion, the Allies had achieved complete air superiority over the battlefield. This was essential for the success of the invasion. Without the P-51 Mustang, the strategic bombing campaign might have failed, and D-Day might not have been possible. But what parts of the story are still in the shadows? What was the real extent of the political infighting between North American Aviation, the Allison Engine Company, and the U.S. Army Air Forces, which initially resisted the idea of using a British engine? Are there any recently declassified test flight reports that detail the dangerous and unpredictable flight characteristics of the very first Merlin Mustang hybrids? How many less successful engine airframe combinations were secretly tested before the perfect match of the Mustang and Merlin was found? Number 4. How do you hide a city to build a bomb? The most secret and ambitious engineering project of the entire war was the Manhattan Project. Its goal was to build an atomic bomb. But before they could build the bomb itself, they had to create the fuel for it. This meant producing enriched uranium and plutonium. This was an industrial and engineering challenge on a scale never seen before. It required building entire secret cities, staffed by tens of thousands of people who had no idea what they were working on. The main site for uranium enrichment was in a remote valley in Tennessee. It was a city called Oak Ridge. In 1942, it was just farmland. Within 2 years, it was a fenced-off, secret city with a population of 75,000 people. It was the fifth largest city in the state, and it didn't appear on any map. At Oak Ridge, they built two massive, completely different types of factories to separate the rare, fissile uranium-235 isotope from the much more common uranium-238. The first was the Y-12 plant. It used a process called electromagnetic separation. It was essentially a giant mass spectrometer. It used thousands of huge electromagnets whose coils were wound with thousands of tons of silver borrowed from the US Treasury because copper was in short supply. These magnets, called calutrons, would bend a stream of uranium ions, and the slightly lighter U-235 ions would bend a tiny bit more, allowing them to be collected. The process was incredibly inefficient. The machinery was constantly breaking down. But it worked. The building was one of the largest in the world at the time. The other plant was K-25. It used a process called gaseous diffusion. This involved pumping a corrosive uranium gas through a series of thousands of porous barriers, or filters. The lighter U-235 gas molecules would pass through the microscopic holes in the barrier slightly faster than the heavier U-238 molecules. To get a significant level of enrichment, the gas had to be pumped through thousands of these stages. The K-25 building was a U-shaped structure, half a mile long on each side. It was the largest building under a single roof in the world. The engineering challenges were immense. They had to develop new kinds of pumps and seals that could withstand the highly corrosive uranium hexafluoride gas. The entire system had to be vacuum tight. The second element for a bomb was plutonium. This was created at another secret site, the Hanford Engineer Works, in a remote part of Washington state. Here, they built the world's first large-scale nuclear reactors. These reactors would irradiate slugs of natural uranium, transforming some of the U-238 into plutonium. Then, the plutonium had to be separated from the intensely radioactive uranium using a complex chemical process. This was done by remote control in massive concrete buildings called canyons, with walls that were several feet thick. The scale of this secret industrial empire, as detailed in Richard Rhodes's definitive book, The Making of the Atomic Bomb, is almost impossible to comprehend. It consumed a huge fraction of the nation's electricity. It involved hundreds of thousands of people, most of whom worked under a strict policy of compartmentalization. They only knew their specific job and were forbidden from discussing it with anyone. It was a feat of civil, chemical, electrical, and nuclear engineering on a scale that has never been repeated. But what secrets did these secret cities keep? What were the most serious nuclear accidents or chemical spills that occurred at Oak Ridge and Hanford, and how were they covered up to prevent panic? Are there any records of the elaborate counter-espionage operations that were run to find and neutralize spies trying to infiltrate these sites? What were the long-term health effects on the thousands of workers who were unknowingly exposed to radiation and toxic chemicals? And is the full extent of this tragedy still unknown? Number 3, how can a ship be built faster than it can be sunk? In 1941, the Battle of the Atlantic was raging. German U-boats were sinking, Allied merchant ships faster than they could be replaced. Britain was an island nation, completely dependent on imports of food, fuel, and war materials. If the U-boats succeeded in cutting this lifeline, Britain would be starved into surrender, and the war would be lost. The Allies needed ships. They needed a lot of them, and they needed them fast. The answer was the Liberty ship. It was not a beautiful ship, it was not a fast ship, it was a basic, no-frills, mass-produced cargo ship. It was designed to be cheap and quick to build. The original design was British, but it was adapted and perfected by American shipyards under the leadership of industrialist Henry J. Kaiser. Kaiser was a construction magnate, not a shipbuilder, and he brought a fresh perspective to the problem. He applied mass production techniques to shipbuilding in a way no one had ever done before. The traditional way to build a ship was to lay a keel and then build the ship piece by piece, from the ground up, in its slipway. This was a slow process. Kaiser's engineers changed everything. They used prefabrication. Large sections of the ship, large technique, the bow, the stern, the deckhouse, were built separately, all over the shipyard at the same time. These massive modules weighing many tons were then brought to the slipway by giant cranes and welded together. This was another key innovation. Traditional ships were riveted, which was a slow, labor-intensive process. The Liberty ships were welded. Welding was faster and used less steel. The results were incredible. At the start of the program, it took over 200 days to build a Liberty ship. By the end of 1942, Kaiser shipyards had cut that time down to an average of 42 days. In a famous publicity stunt, the shipyard in Richmond, California built one Liberty ship, the SS Robert E. Peary, in just 4 days and 15 hours from the time the keel was laid to the time it was launched. It was an assembly line on a gigantic scale. The story of this industrial miracle is told in L.A. Sawyer and W.H. Mitchell's series of books, The Liberty Ships. Over 2,700 Liberty ships were built in American shipyards during the war. They formed a bridge of ships across the Atlantic, carrying millions of tons of cargo. They were the backbone of the Allied supply chain. They delivered the tanks, planes, and fuel that supplied the invasion of Europe. They were a simple, rugged, and expendable design. The early welded hulls had a tendency to crack in the cold waters of the North Atlantic, and some ships broke in two, but the design was improved. They were built to do a job, and they did it. They were a triumph of production engineering. They won the Battle of the Atlantic not by being better than the U-boats, but by outproducing them. There were simply more ships than the U-boats could sink. But what are the untold stories of this massive effort? How many shipyard workers were killed in accidents caused by the frantic pace of production and the use of inexperienced labor? Specific engineering solutions developed to fix the problem of the hulls cracking, and how close did this critical flaw come to derailing the entire program? Are there any surviving personal letters or diaries from the merchant marine sailors who crewed these slow, vulnerable ships, describing the constant terror of sailing in a U-boat-infested ocean? Number 2, can you read an enemy's mind? The German military believed its communications were secure. They used a machine called Enigma to encrypt their messages. The Enigma was a complex electromechanical device that used a series of rotating wheels and a plug board to scramble a message into what seemed like random gibberish. The number of possible settings was astronomical, in the trillions. The settings were changed every day. The German High Command was convinced that the Enigma code was unbreakable. They were wrong. The breaking of the Enigma code was one of the greatest intellectual feats of engineering and mathematics of the war. The story begins in Poland. Polish mathematicians, including Marian Rejewski, had made the first crucial breakthroughs in the 1930s. They shared their work with the British just before the invasion of Poland in 1939. At a secret facility in Britain called Bletchley Park, a team of the country's most brilliant minds, mathematicians, linguists, and chess champions set to work. The key figure was the mathematician Alan Turing. Turing was a genius who laid the theoretical groundwork for modern computing. He and his colleague Gordon Welchman designed a machine called the bomb. The bomb was not a computer in the modern sense. It was a specialized electromechanical code breaking machine. It was designed to rapidly test thousands of possible Enigma settings. It worked by simulating the action of multiple Enigma machines wired together. The operators would use a likely piece of text, a crib, like a standard weather report, that they suspected was in the message. The bomb would then churn through the settings, looking for a logical contradiction. When it found one, that setting was ruled out. When it stopped, it meant it had found a possible correct setting. The engineering of the bomb was a massive task led by Harold Dock, keen at the British Tabulating Machine Company. Each bomb was a 7-foot-tall, 7-foot-wide cabinet filled with dozens of color-coded spinning drums that simulated the Enigma rotors. The wiring was a nightmare of complexity. Over 200 bombs were built. They ran 24 hours a day, their constant clicking sound filling the huts at Bletchley Park. The intelligence gained from breaking Enigma, codenamed Ultra, was invaluable. It gave the Allies a window into the minds of the German High Command. They knew where U-boats were planning to attack convoys in the Atlantic. They knew the strength and position of German forces before the battles in North Africa. They knew details of the German defenses in Normandy before D-Day. As described in F.H. Hinsley's Official History, British intelligence in the Second World War, ultra-intelligence, had a decisive impact on the outcome of almost every major campaign. Later in the war, the British faced an even more complex German code, used by the High Command, called Lorenz. To break this, they built the world's first programmable electronic digital computer Colossus. Designed by Tommy Flowers, Colossus used over 1,500 vacuum tubes and could read a paper tape at 5,000 characters per second. It was an engineering marvel that was decades ahead of its time. The work at Bletchley Park was the birth of the information age, a secret triumph of intellectual engineering. But the secrecy was so complete that huge questions remain. What were the other, less successful, code-breaking machines designed at Bletchley Park that have been completely lost to history? How did the intense psychological pressure of this secret work affect the personal lives of Alan Turing and the other brilliant minds who were forbidden from ever speaking about their achievements. Are there any ultra messages that have still not been declassified containing information so sensitive that it remains hidden even today? Number 1, what happens when you engineer a star on Earth? This was the ultimate question, the ultimate feat of engineering, the culmination of the entire scientific and industrial effort of the war. Could you build a weapon that harnessed the power of the atom itself? In 1939, a group of scientists, including Albert Einstein, warned President Roosevelt that the German government was conducting research into nuclear fission, and that it might be possible to build a bomb of unimaginable power. The race was on. The Manhattan Project, led by General Leslie Groves and the physicist J. Robert Oppenheimer, was the result. As we've seen, it involved building a secret industrial empire to produce the fissile materials, uranium-235 and plutonium. But the final challenge was to design and build the bomb itself. This work was done at another secret laboratory built on a remote mesa in Los Alamos, New Mexico. Here, Oppenheimer assembled an all-star team of the world's top physicists, chemists, and engineers. They pursued 2 different bomb designs. The first was a simple gun-type device. This was for the uranium bomb. It worked like a cannon. A small piece of enriched uranium, the bullet, would be fired down a barrel into a larger piece, the target. When they combined, they would form a supercritical mass, triggering a runaway nuclear chain reaction. An explosion. This design was considered so reliable that it was never tested before it was used. The second design for the plutonium bomb was much more complex. Plutonium produced by the reactors at Hanford had a contaminant isotope that meant a gun-type bomb would fizzle. It would blow itself apart before a full chain reaction could occur. So the Los Alamos scientists, led by figures like Seth Nettermeyer and George Kistiakowsky, had to invent a completely new method implosion. The implosion device consisted of a solid sphere of plutonium, about the size of a grapefruit, surrounded by a carefully arranged shell of conventional high explosives. These explosives had to be shaped into lenses that would focus the blast wave inwards, crushing the plutonium sphere with incredible force and speed. This compression would squeeze the plutonium atoms together, making the mass supercritical and triggering the nuclear detonation. The engineering of the implosion device was a nightmare of complexity. They had to design and test the explosive lenses with incredible precision. They had to invent a new type of high-speed electronic detonator that could fire 32 separate charges simultaneously within a few millionths of a second of each other. If the implosion was not perfectly symmetrical, the bomb would not work. The entire project came down to a single test, codenamed Trinity, which took place in the New Mexico desert on July 16, 1945. The implosion device, nicknamed the Gadget, was hoisted to the top of a 100-foot steel tower. When it was detonated, it produced an explosion equivalent to 20,000 tons of TNT. It turned the night sky into day. The steel tower was vaporized. The sand on the desert floor was melted into a green radioactive glass, later named Trinitite. The test was a terrifying success. Less than a month later, these 2 feats of nuclear engineering were used in combat. On August 6, 1945, the uranium gun-type bomb, Little Boy, was dropped on Hiroshima. 3 days later, on August 9th, the plutonium implosion-type bomb, Fat Man, was dropped on Nagasaki. The war ended within days. The engineering that had begun in the secret cities of Oak Ridge and Hanford and culminated in the secret labs of Los Alamos had brought the world into the atomic age. But even with so much written, what fundamental questions are still not fully answered? What were the alternative, even more dangerous bomb designs that were considered and rejected at Los Alamos? How many scientists and technicians at the Trinity test site were exposed to dangerous levels of radiation, and was the full extent of the fallout and its health consequences intentionally downplayed for decades? Are there any hidden personal diaries from Oppenheimer, Groves, or other top leaders that reveal their true, unfiltered doubts and fears in the final moments before they unleash this unprecedented power upon the world?